This is our fourth day in this DarkMap meeting, and today's first speaker is John Peacock, who will talk about the new imprints of large-scale structure of CMB.
Good morning, everybody. I want to say a few things about how large-scale structure imprints itself on the microwave background, what we learn about it. So, and how we often present it, that the microwave background is a pure, pristine, linear initial conditions at high redshift. This is true to a high approximation. But as we know, we can only see all this stuff by looking through every piece of large-scale structure that exists. And although that complicates the analysis of the microwave background, it actually means we can extract a lot of information about the structure that's developed around us. And that's, you can see, a very powerful problem. Now, you can categorize this into three different effects in which foreground structure imprints itself on the microwave background. There's Compton scattering, it's an Ives-Lendület effect. There's the ISW, integrated Sachs-Wolf effect, which represents the effects of gravitational potentials evolving with time, changing photon energy. There's microwave background lensing, so foreground structure deflecting the position on the sky of CMB photons. These effects operate on different scales. I won't say much about this today, it operates at high multiples. ISW is a very large-scale effect, and gravitational lensing is intermediate, focusing around multiples of, say, 100. Oh, shit. I think I touched the wrong button. Did it do anything?
No, I don't think so.
Okay. Why did they have these? Yeah, so just to mention, the SZ effect is a very good way of probing ionized gas in the universe. There's two distinct ways in which it does this. One is in the bulk motion of scattering electrons, that gives you a frequency-independent effect, and a more complicated effect where the hot gas itself diffuses photons, as I said. That's a small-scale effect that we can do more. The ISW effect is more interesting. Say a microwave background photon falls into a potential well, gains energy, loses that energy on coming out. If the well is evolving, then there's a net energy change and a temperature change in the CMB. If you think about this in the context of metric perturbations, as we know, there's normally a psi perturbation that alters the time part of the metric, a phi perturbation that alters the spatial part. The integrated is a combination of time, those two potentials. But in normal gravity, they're equal, so it's just proportional to the line integral of the time, the Newtonian potential. That's a very powerful thing to be able to probe directly, as we'll see. CMB lensing rearranges the sky subtly. So here's a realization of a 10-degree patch of microwave background. And if you apply lensing, then you get these small effects which are coherent over several degrees, just shifting position by a few minutes. But that makes the microwave background non-Gaussian, and it allows reconstruction algorithms to operate on that non-Gaussian. If you assume that the intrinsic fluctuations are Gaussian, then you can do reconstruction. And this has been shown to work extremely well. For example, for Wayne who really initiated this whole field, some input, projected matter fluctuations, and including CP temperature and polarization maps, you can pull out pretty well what you put in. It's a remarkable thing. And so we have this astonishing results that Planck has given us, where every hot and cold spot you can see here is a genuine structure, a supercluster of void that existed somewhere the last light curve between us and the microwave background. And our task is to just see what this tells us about cosmology. The remarkable thing is that looks exactly like it should. So here's the power spectrum of those lensing fluctuations. I'll explain later on what quantity one's looking at exactly in the, actually, I should say now. This is color-coded between plus or minus a few percent. What quantity are we looking at here? It's a thing called lensing convergence. And if you think about gravitational lensing more in the context of the shape distortions of galaxies, as in standard weak lensing, this convergence, that number, kappa later on, would be the thing that would give you the ellipticity of the galaxy. So a kappa of 1%, which is, as you can see, a sort of technical value, would correspond to the 1% ellipticity that we sheer people try to measure so hard. But here we get that number directly without having to measure shapes of galaxies or worry about astrophysical complications. So CMB lensing is a much cleaner probe. Okay, so here's basically the power spectrum of that map, suitable multiple dependent weight. The line is the prediction that you would make just from fitting the temperature and polarization data of the CMB. So it agrees beautifully. And it gives us a fiducial combination. This is worth noting. Obviously, we learn principally about sigma 8, normalization of fluctuations. There's a density dependent weighting of that with a quite weak dependence, omega matter to the 0.25. Now, interestingly, the standard model predicts where these signals accumulate, and you can see here that mostly the signal comes around about a redshift of 2, but the kernel is very broad, and there's some contribution to these signals at low redshift. And so this has been quite an industry recently, to which I've certainly contributed, of trying to do CMB lensing tomography. That is to take low redshift galaxy catalogs, cut them into slices, cross-correlate those slices with the CMB lensing map. That allows you to pull out the fraction of the CMB lensing signal that exists at low redshift. So here's results from a paper we did with my student Alan Hang, now off his postdoc a few years ago. And what you see here is for different topographic bins. We go up to a redshift of about 0.8, 6 slices in between. The quantity that's being plotted here tells you something about how well correlated the galaxy fluctuations in those redshift slices are with the CMB lensing. And we'd actually do it in harmonic space. So this is the cross power. You've not met it as maybe a confusing quantity, quite simple to compute. Think about how you would compute the power spectrum, the field, take a map on the sky, you construct its harmonic transform, modulus square the harmonic coefficients, that's the power spectrum. To across power, you simply multiply the harmonic coefficients of 2 different maps, one times the complex conjugate of the other. So that's a quantity that is the Fourier transform of the cross correlation between these. Now, what you can see is it's well measured, and also you can see, I hope consistently, the signal is a little bit below the black line. The black line is the prediction of the Planck fiducial model, so the relatively high density omega matter of 0.315. And basically everything is about 10% low compared to that. As with the total CMB lensing signal, you can ask what the consequence of that is for cosmological parameters. The scale of the signal, obviously proportional to sigma 8. Turns out that a faster power of the density parameter for these low redshift contributions is appropriate to about omega matter to the 0.8. And of course, there are other ways that we mentioned this meeting before of probing those same quantities. Weak galaxy shear has been the principal probe for years. So their dependence on the density is intermediate strength between CMB lensing effects I talked about. So it's a sigma 8 omega matter to the 0.5. And that lensing banana, as they call it, quantified by this combination S8, has historically, since even 2007, been low, so just high 0.7s compared to what Planck is fiducially predicting. A4 or so. And so we've always had these pictures of sigma 8 versus the density, Planck here, the lensing results running somewhat below. Now, as we've seen very recently, the kids team raised their number to the point where it's statistically consistent with Planck, so slightly higher than the bananas shown here, although still on the low side. Still waiting, as we've heard, for results from 6 years of DES data, but the 3 years of DES data was certainly on the low side. So DES, like kids, would need to change their tune completely. Otherwise, we are still going to be left with a still indication from galaxy lensing that things are low on this particular levels. So if you put those together, CMB lensing constraints and the weak shear constraints, you get what I thought was a very striking diagram. This, which was to say that you have sigma 8, it's the normalization, doesn't matter the density, Planck here in green, we have these different density dependencies. So the overall strength of total CMB lensing, the Richard 2 component, is this ivory colored band. The very rapidly changing one, the red one, is the CMB lensing tomography that I showed you. Purple is weak galaxy shear, as it was at least before the recent kids result. And they all coincide very nicely. But to the left of Planck, that is to the low density region. So I thought for a few years on the basis of this analysis that there's a very strong case that Planck had the density of the universe too high. That's fair enough. It's not a huge number of sigma. You can find just about consistently down here that a density parameter of 0.3 and no more. Okay, I just want to mention that we've been able to revisit this sort of analysis with the beautiful CMB lensing data that's come out of the ACT experiment. It does much better than Planck because of its higher resolution. This panel here contrasts Planck on the right with ACT on the left, and you can see first of all the less noise. You can see the mottling here. You can also see this black dot. Most people in the room will know what that is, but if not, that's quantization. So that's CMB photons being removed by the hot gas in a cluster of galaxies. And that illustrates what I said. It's a very small scale phenomenon. So we repeated this tomographic analysis with the ACT data. Suffice it to say that we more or less reproduced our previous Planck result, which was a 10% deficiency in signal. Here it's 7.5% low. So it's still the same indication for a low density universe. And as we know, DESI came along, the analysis of the BEO locations. So here is the money plot from the recent DESI work. This is basically the thing that we often show in BEO work is a measurement of a peak in the galaxy correlations at a particular linear scale. But of course, what's interesting is the angle. The thing you really observe is the angle as it tends. So this is the plot of the angles tended by the BEO scale ratio to the angle that would be predicted in the Planck fiducial model. Oh, actually, no, ratio to best fitting CDM model, and the Planck fiducial model would be up here. So we see again that the angles subtended by BEO at redshifts, anything from 1 down, are apparently slightly low compared to Planck. So once again, we have this picture that a low density universe is preferred. So until earlier this year, I was certainly very much of the view that probably everything in cosmology was going to end up being consistent, provided we accepted that Planck's density had just managed to fluctuate high, and the true density parameter was around 0.3. Then we had all this interesting work on whether dark energy actually evolved. And in March, I have to say, I was really quite persuaded by the consistency, not only of the picture that you got by putting all this evidence together, but also with the supernovae. Since then, though, there's been this bombshell that it looks like the supernovae filter profiles were miscalibrated, and all their Hubble diagrams are systematically error by a few percent. So taking that away, personally, I'm now no longer a believer in evolving dark energy, and I'm really back at this position that it's likely that the universe that we live in is close to lambda CDM with a lower density. All right, so all that was by way of historical tours with what we've been doing in this field. So now I want to show you something new that gives us an additional source of information that hasn't been exploited before. And that is dipoles on the sky. So here we are in a room that's traveling some 0.2% of the speed of light. Why are we doing this? Why is the Milky Way moving so fast? Answer, it's being pulled by the peculiar gravity generated by local large-scale structure. So the universe has a peculiar velocity field. That peculiar velocity field at any location points in the direction of gradients of gravitational potential. So here's the standard equation. The peculiar velocity can be computed if you know the density fluctuation and you weight it, you give it a 1 over r squared weighting and a vector weighting point that allows for the direction where this density fluctuation is. So this is computing the dipole moment as the density distribution around this with a particular radial weighting. Okay, so if we sit in the universe, we see high densities over here, low densities over there. Which way do we move? That way. Right, but now you can turn that argument around and say, this says if I give you the density, you can predict the velocity exactly. Supposing I give you just the velocity, that's the only thing we know. We know that the Milky Way is moving this way at 600 kilometers a second. What does that tell us about the density? It tells us that there must be some dipole moment in density. Obviously, we're moving towards high densities, but it doesn't tell us the full range of variation. All it says is that there's a particular distance from us. There'll be some statistical tendency. So you predict a dipole moment in density, but with some cosmic fluctuation. And the beautiful thing about this is that you predict a dipole moment not just in the density, but you predict a dipole moment in any quantity that's related to the density, and particularly the gravitational potential. So, from the point of view of everything I talked about in the first part, that means that there should be dipoles in the quantities that you can observe in the microwave background. That is, in particular, the lensing convergence, and also showing data on it, but the ISW effect, the heat or cooling of microwave photons. And the great thing is that we actually know the velocity at every point in the universe. How do we know that? We know it from a reconstruction from large-scale structure. And this is done routinely now because any project like DESI or past BOSS that wants to study the BEO signal, it performs reconstruction because the BEO peak correlation function is smeared out by the fact that galaxies have moved. And you can recover most of that by predicting the galaxy motions from the fluctuations that you see within the survey itself. That sounds implausible, it really works. So obviously peculiar velocities can be inferred directly at low redshifts just by using distance indicators like Tully-Fisher or the fundamental plane for elliptical galaxies. So we know for local, several thousand local galaxies very accurately whether they're moving away from us or towards us, because obviously you only measure the radial component of these velocities. And that's illustrated here. So blue is moving towards us, red is moving away from us, and the size of the signal circle shows you the magnitude of the velocity. This is the velocity field in different redshift shells, so going out to radial velocities of 10,000 kilometers a second, upward velocities, that is. And on the right is the prediction of the same quantity from redshift surveys that cover that same region of space. So you just look at the density fluctuations, infer from those fluctuations what the peculiar gravity is and the velocity points in the same direction. And the agreement between these maps is truly spellbinding. So there's no doubt empirically that we can measure radial, we can predict from a galaxy survey the radial component of the peculiar velocity. But in that case, we can also predict the thing we can't observe directly, which is the transverse component. So let's think about galaxy survey. Around every galaxy, we have some hypothesis for the direction of the peculiar velocity. And we expect that peculiar velocity will be aligned with a dipole in any quantity related to the density. So the lensing convergences will be around it will be high here, low there. Gravitational potential will be low here, high there. How do we extract that signal? Well, it's very easy. We just have to line up the peculiar velocities. So you extract a postage stamp of the CMB, either the CMB lensing or the CMB temperature around that vector, and then you do the same over here, and then you rotate this map so the velocity vectors are aligned. And then you should be able to pull out the dipole. Well, okay, here's a walking exercise. You should certainly be able to see a dipole around galaxies in the number density of galaxies. And that has to work because it's the number density of galaxies that was used to predict the peculiar velocity. So this is just a consistency test. And this is done twice actually. For the we're doing this with BOSS data. So here is the low Z sample. Here is the CMAS samples. These are just two different redshift shells around redshift 0.4 and redshift 0.6. These maps go out, you can see, to about 50 degrees, and indeed, high density, low density. So now here's the important thing, that because when you stack the map, there's also a monopole. Because if you just stack galaxy density around the location of galaxies, the map that you're making is actually the two-point correlation function. It's the additional density of galaxies around another galaxy. And that's shown in red up here. And of course, you can predict very accurately from, you know very well for the BOSS survey what the two-point function should be, and that's measured fine. But the new statistic is the dipole. And again, of course, that comes out as it should do. So we're in a position to use this sort of information to apply to the microwave background. So here is the money plot, two money plots, because at the top, what we've done for this is just for CMAS, but the CMAS and low Z look similar. This is stacking the CMB lensing convergence map in this aligned, rotated way around CMAS galaxies, and this is stacking the CMB temperature. In both cases, you see a strong, consistent dipole. Perhaps most interesting is to talk about the SW effect down here. That is the dipole in the. This is genuinely new information. If I hadn't done this rotational stacking, obviously the dipole signal would never have manifested itself. This red spot would just be spread out as initially. So all that you'd be left with is the monopole signal, the cross correlation between the temperature and the galaxy density fields. So that's the thing that's traditionally been measured. But that signal is independent of the dipole, which is additional information. So here's the monopole. You can see there's 0, so it's about 1.5 sigma offset from 0, which is what's been measured previously with this sample. So the very weak detection. But you can see here that the dipole is much more significant than that. say 5 to 10 degrees separation. So we've got a much higher precision information on the ISW effect than has ever been detectable before. And the signal has been sitting there in the microwave sky all this time, just waiting to be pulled out. And it's, I find it really exciting to be able to do this for the first time. The level of these signals is consistent with lambda CDM at low density, at this fiducial 0.3 density. You can use that information to constrain. You can use that information to constrain theories of modified gravity. There's some parameter plots on that, but perhaps given the time, I won't dwell on the details. But just what I want to emphasize is that, first of all, putting all this CMB lens information together is really favouring this lower density universe that particularly Desi is trying to give to us. And something I didn't mention, but is worth just dwelling on, is that the low density is attractive, because in terms of the parameter degeneracies of fitting CMB, if you lower the density, you have to lower the best fitting number, raise the best fitting Hubble constant. So that means, if you want a density parameter just under 0.3, Hubble constant should be about 69. That doesn't close the Hubble tension, but it certainly makes things better than they were. So this has the feeling of truth to me. And finally, I've shown you what I think is this really neat dipole signature that exists in terms of the relation of the large-scale structure, microwave backgrounds and foreground fluctuations, and the fact that we've been able to detect it for this time. Thank you.
Questions?
Very interesting talk, and very nice new result. So if we go back to the stacking figure, so the last the result is this one. So on the bottom figure, we see that the dipole is not that symmetric as in theory. So even your color scale is a little bit off, so the middle is not at 0. And, we cannot see the blue part. So is there some explanation for it, or I misunderstood that it should be symmetric?
It's fine. Remember, as I said, the picture you see here is a combination of multipoles. There must be a monopole, because there's the standard ISW effect that galaxies sit at the bottom of gravitational potential wells, so you would expect some positive change in the CMB temperature as a result of that. And that's a spherically symmetric effect, circularly symmetric. On top of that, there's the velocity-related dipole. But you put the two together, of course, that means this picture is not symmetric, because you're taking something that would be plus and minus, and then adding a positive signal to it, so it enhances the positive part of the dipole visually.
Expected.
Yeah.
Questions? Right there? What is the blue curve? Other way to move
This,
That's it.
that's cosmic variance.
But the direction has no information.
No.
On the same slides on the right, why is there such a difference between, on the bottom, the variance of the monopole, so the variation of the variance with scale between the monopole and the quadrupole? Basically, why is it so small on the small scales of the quadrupole? Dipole, sorry.
Yes. I don't have a one-line answer for that. I mean, that's how it comes out when you.
That's okay, then.
Yeah. No, it is. We're confident from simulations and those errors are correct.
But there isn't like a simple.
No,
This is
that's sorry. I don't have a mode counting argument or anything like that.
Okay.
Some kind of statistics.
Other questions? Okay, thank you so much.